Mhm. Space, no? You could add space.
Yeah, it would, it was essentially. It would.
Yours. Yeah. That's all up to you. Mhm. I'm like, what is that? Can you put it in? Not that great. It started. Yesterday. Today. But we did one. I think that's what you spent sleep. That's why I wanted when I. Itu. Because that's what I want to practice right now. Am I wrong? You are. I know. Oh, so you were there. Yeah. Okay. So I take them off. I was just. Yeah. Oh, I didn't. Oh, you didn't.
You guys.
No, I could go, but I'm gonna stop that. I thought I would.
Gotta get that.
Audio recording, or something like that. Honestly, kind of. There's a way from audio, so is that, yeah, I think you get a negative.
Okay.
And then announce it.
You feel like you're talking to. Yeah, they have to like. They're not.
You know where you're going, it's okay.
But,
Oh, it's a very interesting way to,
with yourself.
If we don't see Jerry, we'll go back.
Yeah, not too bad. Yeah, you guys will probably forget. Okay, but I'm just thinking.
Remember some of it.
Oh, let me see. Go for it. Every And then he's like, it's the first. I know. I'm like, what's okay? I'm like, there is a mostly in college, maybe I'm maybe. Oh my God. No. Oh, okay. Oh, that night before. I'm sure, yeah. Oh, good. Oh my God. I'm like, I was thinking. Oh, no. Yeah. And we need to make it fun. So we need to. Maybe you would want to go back. Yeah, well, yeah. Were you guys a thing? Yeah, for.
Charger, that's the USB. I've not tried any. It's not good.
I asked a question.
I don't have any.
Like, I only have like this family. So.
Oh.
Like,
It's,
like, you want.
yeah, I don't even know why I switched the time.
And they felt good about him, you know?
Working days. Okay. Oh, it's on. All right, let's go get started. All right, good evening, everyone. How's everyone doing today? Good, good to hear. All right, I finally have the midterm project ready for you. I know it's a week late compared to when I said I would, but finally it's here. So we're going to spend the first part of today's lecture kind of talking about this. Now, you do have over a month to work on it, but you know that does not mean that it's you should wait till the last minute. So definitely you want to be working on it over that time. But definitely we're going to talk about today. And I'm just going to talk about what's expected of you, what's going to be, what you're going to do, and what you're going to turn at the end. And then after that, we're going to continue on with our lecture notes on shell and beam elements. So we started a little bit of it last time, but I did want to kind of finish that up today before our activity on Thursday. So Thursday is going to be our next ANSYS activity. It's the first activity that I would kind of consider as a little bit more advanced than the other ones. And it's how to basically use shell and beam. So, this week, I think this is kind of when things ramp up a little bit in the class where, we're, first of all, the activity, the midterm projects will be out there, but the activities are not going to cease. And so we're going to keep doing activities. So you're going to need to balance kind of both the midterm project as well as the activities that we're going to. Okay. Okay. Any questions I can answer before we get started for today? Okay, all right, so let's talk about the midterm project. So this document is posted on Canvas for you to look at. Okay, so if you go to the Canvas site, you go under assignments. There should be a new assignment that's activated now called midterm project. Okay, and we can start to take a look at it. So there are several documents here that I posted for you. So there's the project specifications. There is the rubric. So this is how I'm going to score the midterm project. And then there's also a template for the project report as well. And as well as the CAD files are going to be as well. Okay, so basically the idea with the midterm project is that you're going to be doing a kind of a full, what I consider to be kind of a full finite element analysis on a given part. And you're gonna do all steps, basically up until, everything except for getting the geometry yourself, you're gonna be running all the analysis. So that means, loading the geometry in, choosing material properties, meshing, boundary conditions, running the simulation, showing the results, writing it up, basically everything we've been doing for the activities, except now I'm not gonna be kind of holding your hand throughout the whole process. You're gonna be kind of doing it all yourself, okay? Now, I've kind of designed this project in a way which is kind of, emulates kind of what the expectations would be kind of in a professional or research setting in terms of running your own simulations, in terms of how you're supposed to set it up, how you're supposed to kind of display the results, how you're supposed to kind of talk about it in the report. This is kind of your first, I guess, real FEA kind of assignment project that you do. Okay. Now, the only limitation that I place on you is that, I'm going to choose your geometries this time. So I've given you two geometries that you can possibly work with. And so the first one that I have here is a really interesting assembly of parts. So this is, I call it the office setup. Okay. And so here is kind of a workstation monitor, as well as a chair, as well as some other kind of appendages here that may attach to some other things. Okay. And I have a valve assembly here as well. Okay. So you can choose, so the first thing you're gonna do in the project is you're gonna choose one of these. And so I don't want you to do both. So choose one of these geometries, and then that's going to be the subject of your finite element simulation. Okay. Now, I did get some questions over the weekend on whether or not you can choose your own geometries. So I would hold off on that for now. So for the midterm project, I am going to require that everyone pick either one of these geometries, either the home office setup or the valve. You are going to get a chance to use your own geometry for finite element simulation, but that's going to be for the final project. So for the final project, I'm going to open it up so that you can kind of choose your own geometries, or I'll give you some options if you want me to pick one for you. But for the midterm project, just to kind of keep things consistent for now, I'm going to limit it to just these geometries. Okay, so that's the first thing you have to do is just choose one of these and then run your analysis from there. Okay. Now, the reason I kind of chose these two geometries is that you'll notice that each of these geometries contain many different parts. One more so than the other. The home office actually has quite a few components to it. Okay. And sometimes there'll be nuts and bolts included as well, although I think these are mostly devoid of those nuts and bolts. Okay. So one thing you're going to have to do in this project, more so than any other project, is that you're going to have to suppress large portions of the assembly. Okay. So remember we talked about in activity 2 and a little bit in activity 3, where you have the ability to suppress or kind of keep certain parts of your assembly out of the finite element analysis. And there's oftentimes a lot of really good reasons to do so, because oftentimes you don't want to model a part or simulate a part of your assembly that's not going to be either bearing any load or it's not going to be deforming in any way, because that's just going to add extra cost. And so one of the ways that I'm going to assess you on this midterm project is for you to determine, based on your boundary conditions, based on the geometry, which parts are you going to suppress, and whether or not your mesh is efficient based on the results of the simulation, based on the geometry that you want to do. Okay. So just keep that in mind that there's a lot of extra parts here, and these assemblies were not necessarily designed for FEA to begin with, and so it may be very beneficial for you to, or it's going to be very beneficial for you to suppress a lot of these parts. Okay. Okay, and so for the valve here, one additional difficulty with the valve that's not really present in the other difficulty, or not really present in the other geometry, is that there's a lot of internal surfaces here. And so, if you wanted to apply like a pressure load or apply some kind of boundary condition on an internal surface here, you may have some trouble just even clicking on it because it's hidden here. So, you may find useful, you might find it useful to use this feature in ANSYS called hide faces. Which may be, which you can use to temporarily hide some exterior faces to kind of select ones internally. And so, once the project kind of gets rolling, I can show you guys how to do that as well. So that's just kind of one extra caveat for that. Okay. Well, that's essentially what this project's all about. You're going to choose a geometry. You're going to run the simulations and write the report. All right, any questions on the project so far? Okay, good. Okay, so let's get into the specific requirements for each of these geometries here. Okay. Okay. So the first thing that you're going to need to do for your project is to come up with what I call a project objective. Okay. Now, this is one of the main things that you're going to have to think of your own, because for all the activities so far, I've basically given you the objective. Okay. So basically, the idea with an objective is to come up with kind of a reason why you want to run a simulation on these geometries to begin. Okay. So, a finite element simulation or finite element analysis is never done in a vacuum. And so, a finite element analysis is never run just for the sake of running an analysis. There's always some kind of question or some kind of, issue that the engineer is trying to figure out, and they're running the simulation in order to get that data. Okay. So on a very kind of simple way, so a very simple objective that, you may be able to use for your projects is you want to find out, whether the part is going to fail in practice, or what the stress distribution is going to be. Okay, so think of activity 2 and activity 3, where we ran the simulations to see, whether our bike crank was going to fail. So we ran it, we found the stresses, and then based on the stresses, we were able to make a conclusion whether the bike crank is sturdy enough or not. Okay, so that's a very simple example of what a objective is going to be. And so one thing I want you guys to think of for your project is I want you guys to think of your own objective. So, you're gonna have to use your imagination a little bit. So, imagine, how, a valve like this is going to be used in practice. What are some typical loads that are going to be applied onto it? And think of some objectives that we want to accomplish with your finite element simulation. Okay. So some examples. And so, maybe you're interested in the mechanical stress in a critical area of the geometry. And so, let's take the home office, for example. So let's say that you want to test, I don't know, a situation where someone is going to jump up and down on this chair, right? And so if you're going to jump up and down on the chair, then this little supporting beam here that's supporting the weight, that's going to be under a lot of stress. And so you want to, maybe one of the objectives in your simulation is to find out if your setup here is going to survive that kind of force. Okay. So that's one example of an objective. Okay. Maybe you're checking for failure. So that's kind of almost always an objective for these kind of structural simulations. Okay? Maybe you're interested in the maximum deformation for some reason. Maybe you're interested in, maybe minimizing the cost of production. Okay. And so, be creative with this, and don't just have a simple, we're just testing to see if it's failing, right? So one example that, my undergrads actually thought of last semester is, if you take a geometry like this, right? Typically, maybe a geometry like this, maybe a pipe like this is made of some kind of steel or some kind of like that. But steel is very expensive, very heavy. And so what they did was that, maybe we can make this out of a cheaper material. So they ran a simulation of the same geometry. Their geometry was a little bit more simple, but they ran a simulation on a pipe geometry made of copper. And they applied, pressure loads to it, and they were able to show that yes, this pipe is still going to be okay with copper, and that's going to save some costs, save some production costs in terms of, instead of manufacturing out of steel. Okay. So your objective, think of if you were to come up with a backstory, or think of a hypothesis or reason to run the simulation, that's what you're essentially going to, that's essentially what we're looking for the objective. Now, I will say that, for this project, compared to kind of a typical case, for a typical case, you don't have to come up with an objective. The objective is just whatever you're trying to accomplish with the simulation. So for this one, you kind of have to use your imagination and, kind of make something up. But, it's a good practice to think about, what are you looking for specifically in this finite element simulation? Because the thing with FEA is that, there's a wealth of data, there's a wealth of information that you can obtain from any given simulation. And then depending on what your objective is, that's going to tell you exactly what parts of the data, or what aspects of the data do you want to actually highlight, and that's going to drive the rest of your analysis, the rest of your story. Okay. So spend some time, think of a good objective that you can think of, and then that's going to kind of drive everything into your project. Okay. All right. Any questions on that? Yeah.
Can we change the geometry, like Make the seat pull a little bit.
Of course, yeah, yeah, so that's definitely one thing that you can do too. So if you're gonna approach this objective from a design point of view, maybe you want to modify the geometry as well. Now I will say that, both of these geometries were made in SpacePlane, which is the CAD software within ANSYS itself. And so you should be able to modify the dimensions for both of these geometries using SpacePlane. We're gonna use SpacePlane on the activity on Thursday, so you'll be able to know how to do it. But this, the geometry for the valve might be a little bit easier to modify just because there's less dimensions here. This office setup, might be a little bit harder unless you're just changing the width of this, or the diameter of this post right here. So, but yeah, absolutely, you can change the geometry, or the dimensions, and that can be part of your objectives. All right, any other questions on the project objective? Okay. All right, so that's the first big section of the report. The next big section is going to be what I call the finite element modeling methodology. Okay. So by methodology, I mean things like your choice of materials, your choice of meshing settings, how many elements are in your mesh, your choice of boundary conditions, and how that relates to, your objective. And so basically everything that we've been discussing up until this point in the semester, I want to make sure that, you're choosing appropriate settings for everything to make sure your results are accurate. Okay. And so, the way I always have my students think about this is that, whenever you present or whenever you run a finite element simulation, you report on it, you have to imagine that whoever's going to be reading your report or listening to your presentation is going to be really critical of all the decisions that you're going to make. So they're going to ask, why did you choose that element order? Why did you choose that element shape? Did you run a mesh convergence test? Why did you choose the boundary condition this way? So, think of that from that perspective, where every single kind of decision that you're making in the finite element process, you should be able to justify that in your report, in your presentation of the results. Okay. And so this is the part where you're going to incorporate, everything that we've been talking about in the lecture in terms of, what are the best ways to use the mesh? What are the best boundary conditions to use? What are the material properties, things like that. Okay. So this is a section, I'm going to grade pretty heavily on because, this is kind of the whole point of this class is to, make sure you're setting up these finite element simulations appropriately. Okay. Okay. And if you look at the rubric, let me just jump to the rubric. You can see that I've broken down the methodology into kind of the three main sections here. So I have the material properties, there's going to be a big section on the mesh. And so, mesh I'm going to grade pretty heavily just because we've been talking about the mesh a lot, as well as the boundary conditions. Okay. Okay. And so one thing that's the one thing that you're also going to be required to do in this section is that I want you guys to show a mesh convergence test. Okay. So we talked about mesh convergence testing last week, and so you're going to have to apply that for the project. And we're going to get some practice with mesh convergence tests on the activity on Thursday as well. Okay. Okay. And so again, a significant portion of the grade will be determined based on how you choose to do these things. And you should be able to, explain and justify each of your decisions. So that's ultimately kind of what it will. Okay. Now, with regards to the boundary conditions, just like in activity 3, I want you guys to simulate multiple different configurations. Okay. So I want you guys to not just think of one loading scenario. I want you guys to think of at least 3. Okay. And so, changing the direction of forces, adding forces, changing the constraints. You're going to have to come up with 3 different configurations for your simulation. Okay. All right. So now that may seem like a lot, but just remember that, you can be a little bit creative in how you split up those 3 as well. Okay. And so, you may be thinking, for the home office setup, there's only one way for you to sit on that chair. And so, how can you come up with 3 different scenarios? Because I don't want you to just do, a light person, a medium person, a heavy person sitting on the chair. That doesn't count as 3 separate scenarios. And so when you're thinking of your 3 different scenarios here, I want you to think of, what's maybe like an average use case. Number 2, like maybe what's an extreme use case. My mouse is being really wonky right now, so I know normally it's hard for me to write with this, but especially being here today. Okay. So scenario 1 can be an average use case. Scenario 2 can be an extreme case. maybe you dramatically increase kind of the magnitudes of the loading, maybe you add an extra load, okay? And maybe number three could be what I call kind of a corner case. So maybe not something that may happen often, but is a possibility given the scenario, okay? So a corner case, maybe for the home office setup, I don't know, maybe someone gets really mad and they throw their stapler at the computer monitor, and you want to see whether or not the whole thing is going to tip over. Right? So that could be, not something that happens every day, but it can happen, right? And so maybe that's something you simulate for the. Okay. Okay. Any questions on the finite element methodology? Yeah.
How realistic do these scenarios need to be?
They don't have to be that realistic, and so you can definitely be creative. In fact, I would not mind that. I'm reading like 30 of these, and if they're all like person sits in chair, that's gonna be kind of boring. So if you have Superman punching your computer screen, that's fine too. Feel free to be a little bit creative. All right, any other questions on this section here? Okay. All right, so the next section, I was going to behave. Okay, so next section is going to be the results section. So just like you've been doing for all of the activities, you need to present your results. Okay, and so that's going to be in the form of your color contour plot. So that's going to be your total deformation and equivalent stress. Okay, and so you're going to be showing screenshots of that, just like you've been doing in the activities. So the one thing I will say in this section here is just make sure your screenshots are kind of properly framed. And so, don't take a super zoomed out picture where the geometry is really kind of small in the middle. Make sure it's kind of properly framed. I don't need to see the answers GUI, so I don't need to see all of the settings and all that stuff. Just show me the figures, okay? For activity 4 and activity 5, I'll start to give you guys feedback on your figures just so that you kind of know what I'm looking for the report. I know I've been a little bit lax on that for the activities so far. But that's one thing I'm looking for, is just making sure that your figures are properly framed. They show me kind of the deformation and the stresses and all that good stuff. Okay. But the other thing I'm going to be looking for in this section is not just the screenshots themselves, but you should be able to describe in a text, what exactly is the most important features of your results. Okay. So very rarely do you see a finite element report with just the screenshots of the results. Because there could be a few dozen different things that could be highlighted in the results. So you want to make sure that you explain in the text what's the most important part of these screenshots. And so like some of the things that we've been talking about in the activities. And so what is the maximum deformation? Where does the deformation take place? Does it make sense that the max deformation is occurring there? Same thing for the stress. And so what's the maximum stress? Where is the maximum stress taking place? Does it make sense for the stress to be there? Okay, and all of this can be related back to your project objectives as well. Okay, so for this section here, not only am I looking for are your results well presented in terms of the screenshots, but are you able to interpret your results and connect it back to your problem objectives? Okay, it's just like any good lab reports. For a lab report, not only do you run the experiment, you get the data, but then you also analyze the data, you also comment on the data, you discuss the data in terms of what that means for your overall study. Okay, so that's kind of what I'm looking for here as well. So not only can you get the results and the results look clean, but also can you discuss your results and tell me what it is important about the results relative to your project objective. But usually, if you set up your simulations well, your boundary conditions, your meshings are good, then this section is, more or less just kind of running through the motions. Just kind of make sure you discuss your results in the text. Okay. All right. Any questions on this part here? Okay. Good. And then last part of the report is just conclusions, and so just give me some closing remarks. Usually, usually you kind of tie everything all together. So you go back to your project objective. You talk about do the results of your simulation, do they support your objective or do they not support your objective? Things like that, and summarize kind of the important parts of the report itself. Okay. Okay. All right, so that's basically the end of the document. So the other thing here is I am giving you a template. Okay. So please use the template, you don't have to use that exact, font and stuff like that. I'm not that much of a stickler. But at the very least, use the same, headings for the report, okay? Just so it's kind of organized and kind of easier for me to follow, but, I know some of you are trying to get practice with LaTeX, for those of you who are doing research. Or if you prefer a different font, that's fine too. The only thing I ask is that you just use the same headings in the same order that's in the template. But font size, spacing, I'm not too much of a stickler on that, but as long as you're consistent and looks clean, I can read it. And you use the same headings, that's all that kind of matters to me. Okay. People ask every year, what's the page requirement? So there's no page requirement, and so it's going to depend on kind of your objective and how many screenshots that you put, and the formatting, of course. But generally, for on average, what I see for for most reports that do well, they answer all the questions. There's enough content there. They're not rambling on. The page count ends up being roughly about 12 to 15 pages, and that includes the figures as well. Okay. Now, I've seen reports that try to push the page count. They're like 70-page reports, and they have figures that stretch the entire page, and there's 50 different figures, and so that's not an enjoyable experience for me to grade. And so try to be be a bit judicious in terms of the amount of figures that you put in, and just make sure it all tells a clean story. Right? And make sure you include enough detail and enough explanation so that you answer all of the objectives. Okay, so you guys are grad students, and so I know it's there's less for me to discuss with you guys than the undergrads. The undergrads have a lot more questions on these things typically, but I trust you guys to kind of write. You guys kind of know what you're doing in terms of writing. Okay. Okay. I also posted the rubric, so we'll go over that in a second. Last thing I want to say is teams, and so there are no teams for this project, so everyone's going to do their own. Now, granted, because there are only 2 geometries, that means there's going to be a lot of overlap, and so you definitely feel free to talk to your friends and kind of get feedback on there. But everyone's going to write their own report. Everyone's going to do their own simulations. There's no teams for this. All right. Any questions on just the on this before we jump to the template and the rubric? Yeah.
Can you go to that office chair?
What's it?
Oh, can you go to that office?
Yeah. Mm-hmm.
That arm thing?
Yeah, so this arm thing, so I found this geometry online, honestly. This arm thing here could be something that attaches to maybe like a bigger system here. That might be where they kind of run the cables in for the system. It could also be used just to maybe hang something on the back end there, in case this is like a workstation for like a medical hospital. And so they may hang some other equipment on there as well. I can imagine that being the case, but you can also use your imagination in terms of what that extra hook there is there for. You can also just suppress it. So if you can't think of a good application for it, you can just suppress it and then just focus on the other parts of it. All right, any other questions? Yeah.
And we have more than 3 loading conditions?
Of course, yeah, you can have more than 3. I'll grade your 3 best, but you can definitely have more than 3.
And can we use any metric systems field like SI or whatever?
Oh yeah. Any unit system, any material, as long as it's I know I said you can be creative with the loading. You can be creative with the material properties as well, but it should be somewhat believable. So don't use like vibranium or something. Any other questions? Okay. All right, so let's jump to the rubric. I know I kind of flashed it really quickly. But this is the rubric I'm going to use. So basically, once the project is turned in, I'm going to use it to kind of grade all of your projects here. So you can kind of see the point breakdown here, and you can see the sections here kind of correspond to each of the sections that are in the template. So that's why I kind of ask you to use the template, just so it's easier for me to kind of grade each section. Okay. So first thing on the rubric here is the abstract. And so abstract is just a concise summary of the entire project with the principal conclusions. So anytime you read kind of a scientific report, there's always an abstract section. It's kind of I call it the elevator pitch. So if you were to describe a project to someone in like a minute, you would just read them the abstract. Okay. Introduction, this is where you kind of go a bit more into detail of the background of your geometry. This is when you describe your objective, right? And so this is kind of what I'm looking for here. Then we have the three sections on the methodology, and so we've kind of already gone through this. So material properties, meshing, and boundary conditions. Okay. We have your finite element results. So your first configuration, second configuration, third configuration here. Discussion. So there are some discussion questions I want you to answer based on your simulation results based on your study. Okay, so those are all in the template. Conclusions, and then just general aesthetics, and so just making sure the report is clean, it's well organized, it's there's limited grammatical errors, no typos, and all of this. Okay. Okay, and then the template. Let's look at that really quickly. Okay, so this template is a Word doc, but if you want to copy and paste this into Google Docs or use LaTeX, it's fine. Just just use the same headings. Okay. Okay. So you can see all the different sections here, and then I think in each section I kind of describe kind of what I'm expecting. And then for the discussions for the discussion section here, I have these three questions here. Okay. Now for the discussion section here, I know probably I don't have to tell you guys just because you guys are grad students. But for my undergrad, what they did sometimes is they just literally list these three questions and just treated it as if it were like an exam. Just said, here's the question, here's my answer to that question. So, remember, this is a technical report, and so you don't there's I'm having these questions here to help guide your discussion, but don't literally just answer the questions as if it were just like a free response section. Okay. And here are the conclusions. References. I don't think you'll have references unless you want to reference the lecture notes. That's fine. But if you're bringing in some references for outside material properties or some loadings, you can refer to them here. Okay. And I have just some formatting guidelines for figures and figures. Okay. Oh, one last thing. So I know I mentioned at the beginning of the semester, but my expectation is that the reports will be fully written by you guys, and so no ChatGPT, Titan GPT, and so at all. So please just write the reports. If you're having trouble writing the report, just let me know. I will help you, but no AI, just like what we said.
For referencing like lecture notes, how do we format that?
Say again, Louis?
Yeah, so if we're gonna like reference lecture notes or lecture slides, how would you want us to format that, or have it be dictated?
Just say EGME 540 lecture notes, then that's fine.
All right, cool.
You don't have to. I know that you're referring to them because you're in the class, but some people like to mention it in the references. But so yeah, if you want to do it, just say EGME 540 lecture notes spring 2020. Cool. All right, so that's the project. So remember that is going to be due about a month from now, so April 4th. Exactly 1 month. So originally it was due the week prior, but I know that week is when the comp exam is, and so I pushed it a week back just to give the comp exam people some extra breathing. Okay. Now I do think this might be during spring break. I may not. I may be mistaken. So you basically have spring break to work on this. Now that doesn't mean that you wait until spring break to do it. And so I definitely encourage you to work on this beforehand, because spring break, I'll try to be available. I don't plan on traveling this spring break just for personal reasons, so I'll be near my computer, but I'm not going to be answering emails very diligently over spring break. So I would definitely encourage you at least to get all your simulations done before the spring break. And so if you have to, you spend the spring break just writing the report. But try to get everything done beforehand. Okay. All right. So let's go back to the lecture. Okay. So let's go ahead and continue our discussion from last Thursday. So last Thursday we were talking about shell and beam. Okay. So shell and beam elements, just like we discussed last Thursday, these are special element types that you can use in finite element simulation. And so what's unique about these element types is that they are not, even though you're going to use them in a three-dimensional application, a three-dimensional scenario, these elements themselves are actually lower dimension. Okay. So shell elements are specifically two specialized 2D elements. And beam elements, these are specialized one-dimensional elements. And so again, these are special element types that are used in FEA, specifically three-dimensional FEA. Okay? And the situation where you want to use these is, for when you basically use these element types for when you have geometries that are normally very challenging to mesh with solid elements. And so by solid elements, I mean, our traditional tetrahedrons, hexahedrons, the elements we've been using in our activities so far. Okay, so what do those situations look like? So what are situations which are difficult to mesh with the solid elements? So there are two kind of categories of geometries that kind of are in this in this regime here. Okay? The first one that we have is what I call thin geometries. So these are geometries where one spatial dimension or one kind of geometric dimension of your part is much, much smaller than all of the others. Kind of the example or kind of the quintessential example that we have here is a thin plate. So for a thin plate here, we can see that one of our dimensions here, or the thickness of the plate, is much, much smaller than the other ones, okay? The other type of geometry where this kind of falls into place, for the most part, are slender geometries. And so slender geometries are situations where one dimension is actually much, much bigger than all the others. basically, whenever you have a geometry where, you have dimensions that are not kind of fully balanced, right? That's usually a case for when you want to use shells or repeats, right? And the main reason for this is that if you were to try to mesh this with solid elements, there's a general rule of thumb that, that we like to use in FEA called, well, I call it the multiple elements through the thickness rule. And so you never want to have a situation in your mesh where your mesh is just one layer deep, one layer of elements deep. Okay. Right. And so if you were to have, mesh that looks like this, right? So maybe you have mesh elements that kind of look like this, right? Right. So this would be kind of a no-no, right? So in this case, your elements are only kind of one layer deep. So generally, if you are going to use tetrahedrons, hexahedrons, you want to make sure that you have kind of multiple layers of the elements. And remember, the reason that we want to do this is because we want, anytime you run a finite element simulation, you want a healthy number of interior nodes. And so if you only have one layer of elements, then all of your nodes are exterior, which, may not be the worst thing. But, this does make it so that, when you compute certain quantities like the stresses or any derivative based quantities, then it is going to be a lot more inaccurate. All right, so the way to get around this situation, because if you have a geometry that's kind of sufficiently thin or very slender, sometimes it's very difficult to get the situation on the right, because in order to get the situation on the right, you may have to reduce the size of the elements kind of very significantly, and you kind of end up with a mesh with way too many elements for how complex the geometry is. Okay. So while you ideally want to achieve what's on the right, sometimes practically that's not possible if you have a very kind of thin geometry. All right, so for certain types of geometries here, you're kind of stuck between a rock and a hard place. So either, to use the terms that we typically use, either you mesh the shit out of it and you reduce the size and you get really tiny elements. But your computer may blow up if you do that, or you just kind of eat the bullet and say, I don't want to pay the cost, and so I'm going to have inaccurate results. And then you open yourself up to criticism from other people as well. Right? And so the best way to kind of deal with this is to use these kind of specialized shell elements and beam elements for your application. So what we talked about last time is that what's special about shell and beam elements is that they compute extra degrees of freedom at their nodes relative to the solid elements. And those extra degrees of freedom, most notably kind of the rotation of the nodes or the change in orientation, that helps to compute these derived quantities much more accurately without the need for the interior nodes. Okay. Okay. So all that sounds good. So that's kind of everything that we talked about last time. Any questions on any of this? Okay, good. All right, so then the question is, when should you use shell and beam elements? And so, all this sounds great. So why don't we just always use shell and beam elements? Well, there's some limitations on this as well. The question is, can we always use these things? And so, intuitively, you would think no, because, you would think that, you're using a two-dimensional element. You should only use it for geometries that look two-dimensional. Same thing for beams. And so for beams, you should only use it for geometries that look like they're one-dimensional. Okay. So there are actually some significant limitations in how we can apply this. Okay, so the first limitation, so let's talk about shell elements first. So the first limitation for shell elements is that, the assumption is that throughout your entire section of the geometry which you're turning into a shell, the assumption is that the thickness is uniform throughout that entire piece of geometry. And that's actually more difficult to obtain than you think, because anytime you have a filleted region in your geometry, where you have kind of a curved section, where you have a section where the thickness is going to vary, that actually makes it difficult to run some shell elements. Now the shelling tool within ANSYS is a little bit intelligent. And so if it is just a simple curve with a simple fillet, it should be able to figure that out and turn it into a shell. But I will say right now, for your midterm projects, for both options, it's going to be very difficult to obtain shells for that one. The only one where I think you might be able to use a shell is the valve. But even that one, there are weird sections where the pipes kind of meet, which are not kind of uniform thicknesses. So you might have a difficult time creating a shell in those geometries, right? So generally for shells, the assumption is that we only use them when the thickness is consistent, okay? Which is very difficult to do for complex geometries where thickness kind of changes pretty dynamically. Okay. Okay. And same thing for beams too. So the one thing for beams that we're going to talk about is that when you construct a beam element, the beam has to remember information about its cross-sectional shape. And so same thing with the shells, where when you extract a beam, the cross section has to be uniform throughout the entire beam. And now, there are exceptions to this. And so if you have a beam with just a very simple taper, and so it's a beam where, the cross-sectional area will maybe kind of reducing linearly down the length of the beam, you might be able to create a beam out of that one. That's not too bad. But if you have a geometry which is, where the cross-section is kind of changing rapidly or it's changing shape, then that one, you most likely are not going to be able to create a beam out. Okay. All right, number 3. Number 3 is not really a hard rule, but it's just kind of my own personal kind of rule of thumb, is that there must be a sufficient amount of dimension mismatch in order for you to use a beam or shell. Okay, and the threshold that I typically use is that there should be kind of a 10x difference in the dimensions in order to apply a shell or a beam. Yes. And so what I mean by this is that, the thickness should be at least 10 times smaller than your other dimensions in order to apply a shell. Or the length of your beam should be at least 10 times longer than the other dimensions of the cross section in order for you to apply a beam. Okay. So that's my rule of thumb, just because 10 is an easy number to remember. But there are situations where, of course, if it's 9x difference or 8x difference or 7x difference, that might be enough to justify. Granted, the thickness or the cross section remains constant, but you should kind of be in that ballpark. Otherwise, you start to lose a lot of that spatial variation. Because the thing to remember is that when you turn a geometry into kind of shells and beams, you kind of lose the ability to simulate any kind of spatial variation in that dimension that you're using. So that means you can no longer solve for any variation of stress through the thickness of a shell element. Okay, you can no longer compute differences in the deformation across the cross section of a beam. Okay, you're literally taking these geometries and you're kind of removing a dimension, so you're turning into a shell or you're turning into a beam. And so if that variation is important, then you want to make sure that you retain that. You don't turn it into a shell or a beam. Okay. And so a lot of these, are, once you kind of start getting used to these and you start getting used to them, you'll be able to have the intuition to make a judgment call. If you're not sure, honestly, I would say just use the solid elements. That's generally the safer option. You should only use shells and beams in situations where it's kind of fairly obvious. Okay, any questions on this? Okay, all right, so that's kind of the theory behind shells and beams in terms of how they work. Let's talk about kind of the practical side of how do we actually start to apply these in our FEA. Okay, so in other words, how are we even going to do this in the activity on Thursday? Okay, so there's kind of two schools of thought, or kind of two main methods to creating shells and beams within FEA. And the same can be true of the beams as well, although the specifics of the approaches are kind of different. Okay, so the first approach is the first approach is generally the more reliable one, the one that gives you kind of the most accurate results, is to design your geometry from the ground up using shells and using beams. So there are tools and kind of techniques that you can use in the CAD software, and you're not just limited to ANSYS, and so you can definitely use these in SolidWorks as well, where you create kind of a two-dimensional structure. Either you extrude kind of a sketch, an open-ended sketch, and so it doesn't kind of form a complete solid. Maybe you create just a 2D sketch yourself, and then you assign that as a two-dimensional surface, right? And so if you can design your CAD model from the ground up, to have these kind of thin geometries, that's a great way to do it. Okay. That's not what we're going to do, but if you do have that luxury, it is really nice. Okay. The second way to apply a shell or beam is to modify an existing CAD geometry that has three-dimensional parts. Okay. So number two is what we're going to be using in the activity on Thursday, because I'm going to be giving you a geometry, and then you're going to be modifying it to include shells. Okay. So there's a few different ways to do this, right? The easiest way to do this is to apply what's called a mid-surface operation. And so we're going to be doing this a lot in the activity on Thursday. Okay. So the idea with the mid-surface is to take kind of two parallel facets or two parallel faces in your geometry, and then kind of eliminate the thickness between them and replace them with a surface in the middle. Okay. So it looks something like this, and so let's say that we have a geometry in our CAD file. This. It's relatively thin geometry here. Okay. I do it vertical just for a change of pace. And so what we have here is that if you look at one of these surfaces, right? This surface here that's highlighted in red. What you're going to do in the software is you're going to label this as surface number 1. Okay. Then on the back side, which you can't really see because drawing skills or lack thereof. Okay. There is a second surface that is parallel to this first one. All right. That's separated by that small distance. So surface 2, or surface 1 and surface 2. So surface 1, surface 2, they're parallel and they're separated by a distance. We'll call it T for the thickness. All right, so after selecting surface 1, surface 2, and the program kind of confirms that they are indeed parallel and they are separated by a constant distance T, what you can then do is that you can apply mid-surface. And what that mid-surface is going to do is that it's going to eliminate this 3-dimensional object and replace it with a 2-dimensional shell. All right, and so what that's going to look like is that it's gonna basically create a surface right in the middle of these, hence the name mid-surface. So I've gone ahead and drawn that kind of purple line there. Okay. Right, so you have this kind of new kind of shell surface that kind of forms right in the middle of these two. It's going to eliminate the thickness of the other ones, and then all you're going to be left with is just that shell element right in between the two. Okay. All right. And so that's kind of a very common way to produce shell elements from an existing geometry. And you're going to be using this a lot, especially just because, a lot of times when a CAD model was made, the CAD model was not really designed for FEA. And so, if you want to use shell elements or beam elements, you have to kind of work with the existing CAD, which is kind of what we have. Okay. Now, of course, this does mean that you're going to be losing the thickness information. I guess maybe the better way to say is that the thickness information isn't lost. Now it's no longer being represented geometrically, but instead it's being stored in as a material part. Okay. So we're going to be doing this a lot on Thursday. Right? Any questions on mid-surfacing? Okay. So one thing to keep in mind, and you're gonna be dealing with this on Thursday as well, is that when you're using these operations like mid-surfacing, like beam extraction, okay? You're gonna be losing some geometric information. So what that basically means is that, after you eliminate this geometric thickness, some parts of your assembly may not connect in the same way that they've done before. And so to fix this, you're gonna have to kind of manually kind of adjust your geometry. So actually, the majority of the time on Thursday is going to be spent actually fixing the geometry. So, we're going to be, creating shell and beam elements, which is going to, be with the intent of making our finite element simulation better. But it's going to create some problems in other areas as well. Okay, so that's shell elements. And so let's just go over quickly how to get beams. And so once again, with beam elements, there are kind of two main approaches to getting a beam element for your FEA. Okay. And so the first approach is to kind of design the CAD model from the start with beam elements in mind. The other way to approach this is to take an existing CAD model and basically, create beam elements from that. Okay. So thankfully, the process of getting a beam element from an existing CAD model is a little bit more straightforward than mid-surfacing. And so to do this, we're going to use a tool called beam extraction. The way beam extraction works is that you're going to look at your geometry. You're going to see which portion of the geometry or which parts of the geometry would be good as beam elements, and then you're going to activate the extraction tool, and then you're just going to click on the parts that are beams, and then voila, you have beams. And so beam extraction is very simple. I just call it point and click. So let's say that you have a part of your geometry that looks something like this. All you have to do is just click on this, just do beam extraction. And then all of a sudden, now you have a beam. Very straightforward, very easy. Probably the thing we're going to spend the least amount of time on. So when you do the beam extraction tool, information about the cross-sectional shape of the beam is saved within the beam itself. Okay, so just like how shell elements store the thickness as a material property, beam elements also store information about its cross-section within the beam geometry itself. And that's not only just the size of the cross-section, but also the cross-sectional shape. All right, any questions on beam extraction, beam elements here? Okay. One last thing that I want to go over today, just to kind of tie this all together with our discussion of elements, is this idea of using shell and beam elements and mesh convergence. All right, so if you remember from last week, we spent a good amount of time discussing this idea of a mesh convergence test, which basically shows you the convergence or kind of the change in a particular simulation output relative to the number of elements in your mesh. Right. And so generally one of the conclusions from that discussion was that if you use proper meshing techniques, you're going to reach convergence in your results, with fewer number of elements compared to, improper techniques. Okay. What we can say is that it's generally desirable to reach mesh convergence with a fewer number of elements in your mesh rather than both. All right. So let me go ahead and draw a typical mesh convergence plot. Okay, so if you remember, our mesh convergence plot looks like the following. So on the horizontal axis, we have the number of elements. And on the vertical axis, we have usually some kind of finite element result. Whether it be like the stresses or the deformations, max stress, max deformation, average deformation, whatever you think is most important from your simulation. Okay. Okay. So for a typical solid element mesh, and so let's say that we're using hexahedrons, tetrahedrons to mesh a thin geometry, generally what you're going to see is that convergence is really slow, if not impossible. So this pink line here represents the convergence using solid elements. In geometry. And so one thing I'm going to have you do in the activity on Thursday is I'm going to have you do a mesh convergence test on the geometry, but I want you to use solid elements, okay? And what you're going to see, it may not look clean like this, and so it's probably going to be a little bit messy. What you're going to see is that you probably are not going to reach convergence. And so if you look at this plot right here, this plot is not flatlining at all. And so, what this plot is saying is that, we need to go even further beyond the confines of this plot here in order to reach convergence. All right, and that's very common. And in fact, even for your projects, I suspect that, for some of the geometries, most notably the valve, you may have trouble getting convergence. But for the project, it's okay. Those geometries are a little bit more on the challenging side. But the idea is that if you were to use shell and beam elements in a situation where it's appropriate, you should be able to reach convergence much faster. If not, you're going to reach convergence in a situation where normally you may not. So for shell and beam elements, you may have a graph that looks like this. So this blue curve is for shell and beam elements. And you can see from this plot here that we have there's a very clear section where the results start to flatline, where they start to converge, okay? And so what we can say here, usually at this point here, that our mesh is converged at this point. Another way to say is that our results have converged, so we have converged results, okay? So that's generally the expectation. So for situations which are appropriate, which kind of fit all the criteria for using shell and beam elements, you should be able to reach convergence much faster with much fewer elements than if you were to use pure kind of solid elements. And this is kind of the main motivation of kind of why we want to use shells and beams. All right, any questions on this before we wrap it up for today? Okay, all right, so that's all we got. That's all I got for today. So next time I see you guys on Thursday, we'll be doing activity 4. So definitely, look forward to it. And definitely take a look at the midterm project and see kind of which geometry that you want to see. Okay, so thank you guys for coming today. I hope you guys have a good rest of your evening. I will see you guys on Thursday.
In my mind, I'll say, you were 60. This last class, and then I was like, and then you're telling me this, and I'm like, bro, you read my mind. Or basically, I read it. Yeah. I'm so we should not have part of you for it. Oh, I know. No, I'm not.
Yes.
Is there a rule of thumb for advertising, like at least 0.1% your longest?
There's probably some guidelines on it. It's a little bit difficult because it also depends on the loading as well.
Yeah.
And so it depends on which direction the loading is and that. So I would say, usually I go by element count. Honestly, that's usually the metric I go by because it's simpler. So usually for kind of a static structural simulation, for a really good result, I think you usually want to be in the ballpark of like 100, 200,000 units. For a dynamic simulation, you usually want to be a bit more than that. So you want to be like maybe about 300 more. But again, it's going to depend on your mesh convergence. So for certain situations, you may not have convergence at 100,000, 1,000. And so the safest thing is just to run the test. Usually I feel pretty good for a static structural simulation if you're in that ballpark, like 6 figures of element count. That's at least a good start.
100 or 200,000.
Yep. All right, Dominic, ready? So.